Hi, this is Dr. Bricker here with a review for the first exam. The first exam will take place in lab on Wednesday. It's in Su18 E1, which is the lab room. You do get 1.5 hours for the exam, and you provide your own formula sheet. So it's one 8.5 by 11 sheet of notes, both sides. Put whatever you want on there. It just has to be handwritten. So you can't print off parts of the chapter and attach it to a piece of paper or anything like that. It has to be handwritten. So put formulas, example problems, whatever notes you want to put to yourself, words of encouragement, whatever it is, you get one sheet. As far as studying for the exam, I would definitely look at the practice exam. You're watching this video, so that's good. Go back through the homework problems, go back through chapters 1 through 4, skim through the chapters, read the summaries, look at the lecture videos. Okay, very good. I use the practice test as a template for the actual test, so you'll see very similar problems to the homework problems and the practice test problems. Okay, so let's get started. I want to go through these problems, solve them, and then give you some additional hints for problems that you might see. So you won't see the same problems again, you'll just see similar problems, same concepts. The first one here, the acceleration due to gravity on the moon is 1/6 of that on Earth, and the moon has no atmosphere. If you hit a baseball on the moon with the same effect, and it says here that means the same speed and the same angle as on Earth, how far would the ball, how far would the ball travel on the moon compared to the Earth? Neglect air resistance on the Earth. Okay, so it's a projectile motion problem. The gravity on the moon is 1/6 that of Earth, so we could figure out the gravity on the moon from this, 1/6 of the Earth's value. We have a picture that looks something like this. Initial velocity, we would have projectile motion. Here's the angle, and if you remember back from some homework questions, this is the range. And we have something called the range equation. So the range is the initial velocity squared sine of 2 theta divided by g. So we could get an idea what the range would be on the Earth. It would be from this formula, same initial speed. Now if you're on the moon, the range equation still works. It's just that the g of the moon is 1/6 of that of the Earth. So if you look at this, you'd get a certain distance for the Earth. The moon's distance is actually going to be 6 times greater. So if you compare this formula to this formula, because the g's are different, the 6 here in the denominator would pop up to the top, and this value is 6 times as great as that value. So as far as projectile motion goes, that's one of the tools we have, the range equation. We also have a few other things. Let me show you this. I've broken this down into x and y direction. So x and y, for the x direction we only have the x velocity is delta x. Let me write it like that. The x velocity delta x over delta t, and the acceleration to x is 0. Okay, so the x direction is not very complicated. Also, we can't do a whole bunch with it because there's not a lot of formulas here. In the y direction, we have all the kinematics equations. Let me move this out of the way for just a second. We have all kinematics equations. The final velocity is equal to the initial velocity plus at, the final velocity squared, initial velocity squared, plus 2a delta y. And I put the y's here just to emphasize I'm talking about the y direction. Delta y, initial velocity times time, plus 1/2 at squared. And here the acceleration is negative 9.8 meters per second squared. Okay, so the thing that ties the x direction and the y direction together is the time. And we also see the range equation. We've just went over that in the previous problem. So many problems will ask you, what's the maximum height? So take a look at this picture. So if you leave here, projectile motion back down to the ground, the initial velocity in the x, which really I just call it the final velocity in x, or the constant velocity in x maybe is a better way, is the initial velocity times the cosine of theta. The y velocity initially is the overall velocity times the sine of theta. And now at the highest point, that's where the y velocity is 0. All of the other points, the x velocity stays the same. So if you do want to figure out the maximum height, we can take a look at this equation. And we can use the fact that at the highest point, the y velocity is 0. So highest point, y velocity is 0. If you look at this, y velocity is 0. If you know the initial velocity in the y, it's crucial. This is the y, not the overall. This is the y. Plus 2a delta y. You can get the maximum height from this because you'll know this, and this is a given. Now, if you want to figure out how long it takes to get to the maximum height, we can use the first equation here. So at the highest point, again, that's where the y velocity is 0. We'll use that. So if you know the initial velocity in the y, again, that's in the y, plus a times t, then you can figure out the time it takes to get to the maximum height. So this is a review of projectile motion. We started with just the range equation, but really all of this works here. Okay, good. So again, look back through the homework questions dealing with that. Okay, the next question, number 2. Oh, by the way, you know, this is multiple choice, but you still have to show your work. You can't just go through and circle the answers. You'll get 0 points for that. So definitely show your work. Okay, the second one, a rock from a volcanic eruption is launched straight up into the air with no appreciable air resistance. Which of the following statements about the rock while it's in the air is correct? Okay, so before I even start thinking about it, here's what the velocity versus time graph would look like. The velocity starts out positive because it's going up, gets less and less positive as it slows down. At the highest point, the velocity is 0, and then on the way down, it becomes negative. The entire time, though, it's under the influence of gravity, so it's negative 9.8 meters per second squared. And that's the slope of this position versus time graph. Okay, let's take a look at these possible choices. By the way, also, I only on the test give you one of these being correct. It's not like pick whichever one's right. It's just pick the one that's right. There's only going to be one correct answer. Okay, on the way down, both the velocity and acceleration are down. Okay, so that's good. At the highest point, the velocity and acceleration are 0. So that's not true. The entire time, the acceleration is negative 9.8. When you get to the highest point, we don't shut off gravity. It's still there. Choice B, the acceleration is down at all points in the motion. Okay, so that's definitely true. Gravity's always there. Let's see what the other ones hold in store. B, I think, is the correct answer, though. The acceleration is down at all points except it's 0 at the highest point. So that's not true. It's the velocity 0 at the highest point, but you still have acceleration. The free body diagram at the highest point is still this. You still have gravity pointing down. Okay, choice D, on the way up, acceleration is down, velocity is up. Okay, that's good. At the highest point, both velocity and acceleration are 0. Again, acceleration is not 0. Last one, throughout the motion, the acceleration is down, and the velocity is always in the same direction as the acceleration. So that's not true. On the way up, the velocity is up, the acceleration is down. Those are in opposite directions. As far as explain goes, I've got a nice picture here. You could also say A is the slope, acceleration is the slope of the velocity versus time graph, and it's always negative 9.8, and I even have a free body diagram there. Okay, good. So explain doesn't mean you can just use words. You can use graphs, equations, however you get your point across. The next one, which of the following graphs represents an object at rest? And there could be more than one, but again on the test I won't put more than one. Okay, with graphs, the first thing to notice is what's being graphed, position versus time. Okay, so you're at some position and it's not changing. Okay, so that means the velocity is 0. You're at rest. So right away I think that's correct, but let's go through the other ones. Here, the position is changing with time, and you're actually speeding up because the slope of the tangent lines keep getting bigger and bigger. So this is actually accelerating. Okay, position versus time. Slope here is negative. This is a constant velocity, but it's negative. This one doesn't even make physical sense. You go from some coordinate, from 0 to some coordinate in no time. So this is infinite acceleration. That can't even happen. Okay, so this one's a little different. This is velocity versus time. So this is a constant velocity. So you are moving, you've got a constant velocity. This means the acceleration is 0, but it doesn't mean that the object's at rest. It just means that the velocity is not changing. As far as explain goes, several ways of doing it. I put here the object is located at some x-coordinate for the first choice here, and that coordinate does not change, therefore the object is at rest. That's fine. You could also say the slope of this graph is 0. That means the velocity is 0. The object's at rest. So something like that. A few different ways of explaining it. Okay, number 4. Suppose that an object is moving with a constant velocity. All right, we just kind of talked about that one actually. Here's what the picture looks like. Which of the following statements, or which statement concerning its acceleration must be correct? Well, I know it's got to be 0 if the velocity is not changing. The acceleration is a constant non-zero value. Okay, so that's not true. If the acceleration were constant, the velocity would actually be changing. Acceleration 0, okay, that's good. Let's see what the other ones have though. Acceleration's increasing, acceleration's constantly decreasing. Good, so that's not true. We're saying that that's a constant velocity. That means we have this picture, acceleration 0, delta v over delta t, that's what acceleration is. So if it's constant, that means it's not changing, so the change in velocity would be 0. Okay, so we can explain it really. This is probably enough. Add that, it's, that's also good too. Okay, number 5. If the rockets of a spaceship in outer space, far from all gravity, suddenly lose power and go off, the spaceship will gradually slow to a stop. So that's not true. An object in motion will stay in motion unless acted upon by a net force. This is the one that doesn't seem true on Earth because you always do have friction. But if you're really in outer space away from everything, if something's already moving, and that's what we have here, something's already moving, it'll just keep on moving unless there is an outside force to make it slow down. Good, so if something's already moving, you don't have to have a force to keep it moving. If I were to put a force on this object, it would actually speed up or slow down depending on, the direction of the force. So you will see a Newton's first law question. That's what this is. Okay. Number 6, we're about halfway there. A ball is thrown downward from the top of a building with an initial speed of 25 meters per second. It strikes the ground. 2 seconds later, how high is the building, assuming negligible air resistance? Okay, so before I do anything, I want to draw a nice picture, which I have here. Here's the picture. Here's the initial velocity, 25 meters per second. And there's a negative sign there because it's down. I'm given a time of 2 seconds. I've got to bring this information to the problem myself. The acceleration in the y direction, negative 9.8 meters per second squared. And then here's the picture. And I'm trying to figure out the height. So if I can figure out delta y, the displacement in the y direction, the height is going to be the magnitude of the displacement here. So if you have a picture and you have written down, what you're looking for, out of 10 points, this right here is probably worth at least 4 points. We're trying to learn, to organize our thoughts and solve problems, and to do that, I think a picture helps, and the information that we have. You take it from the text here and you write it in this way, it makes it a lot easier to process. Okay, so again, that's about 4 out of 10. And here's the tools we have to use. Kinematics equations. These are for free fall, so I wrote everything in terms of the y direction, and I know the acceleration in the y again, negative 9.8. So I have to sift through these and see what I can use. I'm trying to figure out delta y. Here's one that says delta y is equal to something. Let's see if this works. Initial velocity, okay, I know that, and I know the time, 1/2 acceleration, and I know that's negative 9.8. Again, I know the time. So I can get the displacement here. It's going to turn out to be negative, and the height's going to be the magnitude of the displacement here. Now, if you don't put the negative sign in for the y velocity, you will not get the correct answer, so be careful with that. An alternative way of solving this problem would be to figure out the speed right before it hits the ground, and I could do that from this equation. Because I know the initial velocity, the acceleration, the time, I could figure out the speed right before I hit the ground. And then once I know the speed right before I hit the ground, I can go to this kinematics equation. And then the only thing that I don't know here is delta y. You'd have to do a little bit of algebra to to be able to do that, but then you can solve for delta y. So a couple of ways of solving this problem. Okay, so you'll definitely see a free fall one on the exam. Okay, next one. In an air-free chamber, a pebble is thrown horizontally. Okay, so we're assuming there's no air resistance. A pebble is thrown horizontally, and at the same time, a second pebble is dropped from the same height. Compare the time of fall of the two pebbles. So we definitely need a picture for this one. One, I'm just dropping straight down. The initial velocity is 0, in the y direction, also the x direction. The other one you throw horizontally. So throwing it horizontally also means that the initial velocity in the y direction is equal to 0. It only has x velocity, and they're thrown from the same height. So this is the same. They're both in free fall. The other things that is the same. The initial velocity in the y is 0. So let's get an idea how long these things are going to take to hit the ground. We saw this from the previous problem. Delta y, initial velocity times time, plus 1/2 at squared. Now the velocity here in the y direction for both of them is 0. Okay, so this term is 0. You could multiply both sides by 2, then divide by acceleration in the y, take the square root to get the time. So same initial velocity 0, same acceleration, same delta y. The t's are going to be the same. So you can't just guess on this problem. You have to, show why they're the same. So we'll definitely have the picture, and here we can see that they're the same. Okay, excellent. Okay, let's take a look at number 8. We have a car starts from rest and accelerates at 4 meters per second squared for 5 seconds. Maintains that velocity it has reached for 10 seconds, and then slows down at a steady rate of 2 meters per second squared for 4 seconds. We had a homework problem that was just like this. It was a train that started at one station, sped up, reached the cruising speed, and then slowed down into the next station. And in that problem, we were able to find the total distance covered and the total time. And this is really similar to that, almost the same problem actually. So let's see, we're starting with at rest, so the initial velocity is 0. And in the first part, we're accelerating at 4 meters per second squared for 5 seconds. So this is really just the information for the first part. I kind of have it listed over here. This might be a little bit better way of looking at it. So we start from rest, accelerate 4 meters per second squared for 5 seconds, and that's this part. Then we travel at that speed for 10 seconds. We haven't figured out this 20 yet. We will in just a minute. And then over here we slow down. So if I can figure out the speed I attain after 5 seconds, that's the same speed that we have here, and then we use that speed for the initial speed for the third leg to slow down. So let's see how I got this 20 meters per second. Now if you start from rest and you accelerate at 4 meters per second squared for 5 seconds, every second it increases by 4. So after the first second we would be going 4, another second, then we would be going 8, etc. All the way up until you get to 20. Here's the kinematics equation I can use for this though. The later velocity is equal to the earlier velocity plus at. So v2, which I'm calling the velocity I attain after 5 seconds, how much I start with, 0 plus a times t, so 20 meters per second. So 0 up to 20, maintain 20 for 10 seconds, and then I slow down. So the speed I start this segment with would be 20 meters per second, and every second that decreases by 2 meters per second. And I've got a total of 4 seconds. So if I'm at 20, after 1 second I'm down to 18, another second 16, 14, and 12. Here's the kinematics equation I could use to show you that that actually works. Later velocity is equal to earlier velocity plus at. Now I'm slowing down, so I know in the third leg that's got to be negative 2 meters per second squared. So I have v3 is equal to v2 plus at. And then I can put the numbers in here. 20 plus, don't forget the minus sign, 2 meters per second squared for 4 seconds leaves me with 12 meters per second. So take a look back at the one we did on the homework where it was the train problem. Okay, here's another one. Number 9. A car is traveling with a constant speed when the driver suddenly applies the brakes, causing the car to slow down with a constant acceleration of 3 meters per second squared. So really, slowing down, that means negative 3.5 meters per second squared. If the car comes to a stop in a distance of 30 meters, what was the car's original speed? Okay, so car comes to a stop means the final speed must be 0. So I've got the acceleration here, negative 3.5 meters per second squared, delta x, 30 meters, final speed 0. What did I start with? So here's what the velocity versus time graph would look like. I start here with some speed, I don't know what that is. After a certain amount of time, I've come to rest. Okay? Good, so here's the information that I have. Here's a little extra. This is probably worth, 4 points out of 10 again. Here's the tools I have to use, my kinematics equations. The final velocity is equal to the initial velocity plus at. Final velocity squared, initial velocity squared, 2a delta x. Delta x, initial velocity times time, 1/2 at squared. Okay, so all the equations have acceleration in them. 2 of the 3, the first one and the third one, have time involved. I don't know the time. I do know the displacement, though. So it looks like the second one here I can actually use to figure out the initial speed. Okay? We'll have to do a little bit of algebra. So here we go. Final velocity squared, initial velocity squared, 2a delta x. The final speed is 0, so that's 0. I could move the 2a delta x to the other side and have minus 2a delta x. Take the square root of both sides to get the initial speed. Now if you forgot to put the negative sign here for the acceleration, you would remember now because it's negative 2, and if you didn't put negative for a, something would be wrong. So using this, then you can figure out the initial speed. Okay, so this problem utilized this equation. The previous one, number 8, we used really the first kinematics equation. So just be familiar with the kinematics equations because you'll definitely see several problems on the test with that. Okay, number 10. A ball is thrown with an initial speed of 20 meters per second at an angle of 60 degrees. Okay, so here's what I know. If we can neglect air resistance, what is the horizontal component of the instantaneous velocity at the exact top of the trajectory? Okay, so here's a picture. Projectile motion again. Here's the distance that we're going in the x direction. Here's the overall velocity here. We have an x part, which is vi cosine, vi cosine theta. Initial part in the y, which is vi sine theta. Now the x part, again, is not going to change the whole time. Whatever it turns out to be, it's the same the whole time, the x part. The y part is the part that actually changes. Luckily for this one, they're just asking us, what's the horizontal component at the highest point? Well, it doesn't even matter that they say the highest point. It's the same the whole time. So let's figure out the x velocity. X velocity, initial, cosine theta, so 20, cosine of 60, which is the same as the sine of 30, so it should come out to be 10. So that's the x velocity at the highest point. Also know how to figure out the maximum height. So you're not going to have this exact same kind of problem. Know how to figure out the maximum height. We talked about that in the very first problem. Also be able to figure out how long it takes to get to the maximum height. And again, we talked about that in the first problem. Okay, good. Number 11, the magnitude of this vector is 5.5, lies in the second quadrant, makes an angle of 34 degrees with the positive y-axis. Okay, so this is the vector A. Here's 34 degrees. And we want to figure out the components of A. Okay, so this is the x part of A. This is the y part of A. Okay, and I try to draw pretty much the scale, the angles here. And you can actually go through and do this without doing the trig. You can kind of weed these things out. You know that the x part has to be negative. and the y part has to be positive. So the ones that don't correspond to that, the ones where x is actually positive, would be this one, so we can get rid of this one. And we can get rid of this one, because x is positive in this answer, and from the picture you know it's negative. Y has to be positive, so from the remaining ones, y has got to be positive, so we can get rid of this choice. We also know that the magnitude of A has to be less than the magnitude of x has to be less than the magnitude of y. So we can get rid of this choice because we've got, this is 4.6, that's 3.1. And if you did that and you explain, I went through and figured it out, because the x part's got to be negative and the magnitude has to be less than the magnitude of y, I chose that. That would be fine. Here's the way to do it with actually using sine and cosine. So the sine of 56 would be the opposite side over the hypotenuse here. So, put in 5.5 for A, you would get 4.6. The cosine of 56 would be the adjacent side over the hypotenuse. And I know that x has to come out to be negative. When I use these small triangles, the negative sign's not going to come out. You could use a larger angle, add 90 to this angle to get the correct value. I like to use little triangles and then have my picture and know that this has to be negative. Okay, so then I've put the negative sign in because I know it from the picture, and you get minus 3.1. The only other thing I could add here is if I know the x part and the y part, I could get the magnitude here. So definitely know the sine, cosine, tangent, and then know this Pythagorean theorem as well. So this one I gave you the overall vector and the angle, and you can get the components. Be able to do it in reverse too if you know this side and this side. How much is this? And what is the angle? Okay, so sine, cosine, tangent, Pythagorean theorem. Okay, great. A couple more to go. Let's see, number 12. A bucket is being lowered by a very light rope, so we're assuming it's massless, with a constant downward velocity. So constant velocity is English. Physics means the acceleration is 0. That means the net force is 0. And we want to know the tension, how is it compared to the weight. Okay, so at this point, we're looking at it moving at a constant velocity. To get it moving downward, you would have had to have accelerated it downward, but we're just looking at it now where the velocity is constant. Acceleration is 0. So that means there's no net force. Whatever's up has to be equal to whatever's down. So it's already moving down at this point, and now we have those equal to each other. So net force is ma t minus w. Now if a is 0, this side is 0, t's got to be equal to w. If this bucket were accelerating upward, t would have to be bigger than w. If it were accelerating downward, w would have to be bigger than t. So if whatever direction you have an acceleration, there has to be a net force in that direction. Okay, so I won't give you this exact one, but keep in mind if it were to be accelerating up, this would have to be bigger than this. Accelerating down, this would have to be bigger than that sort of thing. Okay, finally, an object that weighs 75 newtons, so that's its weight, not its mass, that's its weight, pulled on a horizontal surface with 50 newtons to the right. The frictional force to the left is 30 newtons. What is the acceleration? Draw a free body diagram. Okay, so here's the free body diagram, just the forces acting on the object. 50 newtons to the right, 30 newtons to the left. Weight is 75 newtons. Normal force, therefore, has to be 75 newtons. So that's probably 5 out of 10 points right there. So the weight is also equal to mg. So I can get the mass if I need it, which actually turns out I do need it. Okay, so Newton's second law. This is just in a little box over here by itself. Newton's second law, F is equal to ma. 50 to the right, 30 to the left. The net force is 20 newtons. So the acceleration is going to be, if the net force is 20, ma is equal to 20. That's the net force is equal to 20. So then, therefore, the acceleration is 20 newtons divided by the mass. So not divided by the weight, divided by the mass. And we can get the mass because we know mg is 75 newtons. The mass then is 75 divided by g, which is 9.8. So you can take this for the mass and put it in here. Okay, excellent. So again, I use the practice test as the template for the actual test. You'll see very similar, concepts, not the exact same problems, but same concepts. Similar length, multiple choice, but show your work and explain. Okay, you can ask your lab instructor Monday if you have any questions. You can email me. You've got my email address. And should be no problem if you can do the practice test and the homework questions. Okay, thanks, and I'll talk to you soon. Bye-bye.